Once again, welcome back to Physics with Sanoop. Children, now in this video, we will discuss all the previous questions from the chapter Wave Optics. Okay, see, we have all questions that appeared for NEET as well as this AAPMT earlier. Okay, so the first question is interference pattern is obtained with two coherent light sources of intensity ratio n. In the interference pattern, the ratio I max minus I minimum divided by I max plus I minimum will be. Okay, see we have I max by I minimum equal to root of I1 by I2 plus 1 divided by root of I1 by I2 minus 1 whole square. Okay, and root I1 by I2 is root n. So it will be root n plus 1 divided by root n minus 1 whole square, or we can write root n plus 1 whole square by root n minus 1 whole square. See, we want the ratio I max minus I minimum divided by I max plus I minimum, and we have I max by I minimum. Okay, so we can use the component or dividend rule. See, if A by B equal to M by N, then A minus B divided by A plus B, that must be equal to M minus N divided by M plus N. Okay, we have I max by I minimum. Okay, so I max minus I minimum divided by I max plus I minimum. Whatever you do on the left side, same thing should be done on the right side also. So this is numerator minus denominator. So on the right side also, numerator minus denominator means root n plus 1 whole square minus root n minus 1 whole square. In the denominator on the left side, we have I max plus I minimum, means numerator plus denominator. So on the right side also, we should do the same, root n plus 1 whole square plus root n minus 1 whole square. See, this is of the form a plus b whole square minus a minus b whole square, that is 4ab, means 4 into root n into 1, 4 into root n into 1. And in the denominator we have a plus b whole square plus a minus b whole square, that will be 2 times a square plus b square. Okay, 2 times. A square means what stands for the first term a, that is root n square means n, and second term 1 square, that is 1 itself. Okay, we have 4 by 2, that is 2 root n divided by n plus 1, 2 root n divided by n plus 1. The periodic waves of intensities I1 and I2 pass through a region at the same time in the same direction. The sum of the maximum and minimum intensities. See, if I1 and I2 are the intensities of the two sources, then I max is root I1 plus root I2 whole square, and I minimum is root I1 minus root I2 whole square. Okay, so I max, when we expand this, we will get I1 plus I2 minus 2 root I1 I2, and the expansion of this is I1 plus I2 minus 2 root I1 I2. So I max plus I minimum will be 2 times I1 plus I2. So this is the correct option. Okay. Colors appear on soap film and on soap bubbles due to the phenomenon of interference, the color of thin films. Interference was observed in interference chamber where air was present. Now the chamber is evacuated, and if the same light is used, a careful observer will see. See, beta, that is the bandwidth in vacuum, lambda capital D by small d, where lambda is the wavelength in vacuum. If there is air, bandwidth will be beta dash, and wavelength will change. It will be lambda by mu, where mu is the refractive index of air. Capital D by small d will remain unchanged. So beta dash, that is the bandwidth in air, equals beta, bandwidth in vacuum, divided by mu. So bandwidth in vacuum means when it is evacuated. When it is evacuated, bandwidth will be mu times the bandwidth in air. Okay. See, mu, that is the refractive index of air, is slightly greater than vacuum. That is why they say a careful observer. Okay, because there will be a small increase in bandwidth. Okay, interference fringe with the larger width. Okay, beta is the bandwidth in vacuum, and beta dash is the bandwidth when there is air. Okay. Now let's see what we have next. The ratio of the intensities of two waves are given by 4:1, the ratio of the amplitudes. See, for coherent waves, amplitude is proportional to square of, intensity is proportional to square of amplitudes. So A1 by A2 equals root of I1 by I2 means root 4 by 1 or 2:1. So the first option. If the screen is moved away from the plane of the slits in Young's double slit experiment, means capital D is increased. Okay, linear separation of the fringes means that is beta should increase, but they say decreases. So that's a false statement. Angular separation is independent of capital D. Just now I have told you, no? Angular separation of fringes is independent. Okay, linear separation of fringes increases. When capital D is increased, beta increases. Okay, so this must be the correct option. Now children, let's see what we have next in Young's double slit experiment. A student observes 8 fringes in a certain segment of screen when a monochromatic light of 600 nanometer wavelength is used. If the wavelength of light is used, change it to 400 nanometer, then the number of fringes would observe in the same region. See, when 600 nanometer is used, there are 8 fringes in a particular region. How many fringes will be there in the same region if the wavelength is reduced to 400 nanometer? Okay, so this n1 lambda 1 capital D by small d is the region occupied by n1 bands of wavelength lambda 1. It is the same as the region occupied by n2 bands of wavelength lambda 2. Okay, and we will get n2 equal to lambda 1 by lambda 2 times n1, 600 by 400 into 8, that is equal to 12. Okay. In Young's double slit experiment, if the separation between coherent sources is halved and the distance of the screen from the coherent sources is doubled, okay, this is a common question you can expect in the future also. So that is beta equals lambda capital D by small d, beta dash means lambda, this separation of the screen from the double slit is doubled. Okay, d is to be replaced by 2d and small d is to be replaced by d by 2 because separation of the slits is reduced to half. So we will get 4 lambda d by d or 4 times beta. Okay, so 4 times. Now see, in Young's double slit experiment, when the light of wavelength 400 nanometer was used, the angular width of the first minimum formed on a screen placed 1 meter away was found to be 0.2 degree. What will be the angular width of the first minima? Okay, if the entire experimental apparatus is immersed in water of refractive index 4 by 3. See, angular width that is equal to lambda divided by small d, that is equal to beta divided by capital D. Okay, that is beta by capital D. Okay, actually see, I have told you earlier, no, it is independent of capital D. It depends only on lambda and small d. Okay, now see, theta proportional to lambda. Okay, so theta dash will be lambda dash by small d. Small d we are not changing. Lambda will become lambda dash and it is equal to lambda by mu. Okay, so theta dash will be theta by mu. Okay, mu is 4 by 3, so we will get 0.15 degree. 0.15 degree. Okay. Next, in Young's double slit experiment, if there is no initial phase difference between light from the two slits, a point on the screen corresponding to fifth minimum. Okay, fifth minimum has a path difference. See, minimum will be produced when the path difference is an odd multiple of half the wavelength, lambda by 2. So the path difference will be 2n minus 1 lambda by 2, or you can use 2n plus 1 lambda by 2 also. But it is always preferred to use 2n minus 1 lambda by 2, because in this case, when you put n equal to 1, you will get the path difference for first dark bands. When you put n equal to 2, you will get the path difference for second, n equal to 3 for third, like that. But if you use 2n plus 1 lambda by 2, then also you can use that way also. But see, in that case, first dark band corresponds to n equal to 0. Second dark band corresponds to n equal to 1. Third corresponds to n equal to 2. But if you use 2n minus 1, n equal to 1 corresponds to first, n equal to 2 corresponds to second, n equal to 3 corresponds to third, like that. Beautiful. Okay, so here we have to find the path difference for fifth dark bands. Okay, if there is initial phase, a point on the screen corresponding to fifth minimum, means fifth dark band, you have to put n equal to 5, 2 into 5, that is 10 minus 1, 9 lambda by 2, 9 lambda by 2. Okay, The two slits in Young's experiment have width in the ratio 1:25, the ratio of intensity at the maximum and minimum in the interference pattern. I1 by I2, intensity is directly proportional to width of the slits. So I1 by I2 will be W1 over W2, and it is given that 1/25. I max by I minimum, this is root I1 by I2 plus 1, root I1 by I2 minus 1, okay, whole square. So it will be 1/25 under root plus 1, 1/25 under root minus 1. Okay, so 1/5 plus 1, 1/5 minus 1, that will be 6/5 and minus 4/5. By 5 and by 5 will get cancelled. Okay, this and this will get cancelled. So it will be 6 by minus 4. See, as we have to get the square, that minus 4 square and 4 square are the same. So 6/4 or 3/2 whole square or 9:4. Okay, 9:4, this one, right? In Young's double slit experiment, the slits are 2 mm apart and are illuminated by photons of wavelength 12,000 angstroms and 10,000 angstroms. At what distance from the common central bright fringe on the screen 2 meter away, 2 meter from the slit, will a bright fringe from one interference pattern coincide with the bright fringe from the other? See, we are using two wavelengths at the same time in the same setup. So each wavelength will produce its own interference pattern. Okay, and see, there will be points where the bright bands of the two patterns coincides. Okay, so here we have to get the at what minimum distance from the common central bright fringe. Means what is the distance of the first point from the center of the screen where the bright bands of the two wavelengths coincides. Okay, now suppose n1th band of the pattern due to wavelength lambda 1 coincides with the n2th band of the pattern due to the wavelength lambda 2. Okay, so that distance from the center n1 lambda 1 capital D by small d, that is the distance of the n1th band from the center due to the first wavelength, that is equal to distance of the n2th band from the center of the screen due to the wavelength lambda 2. Okay, so we will get n1 by n2 equal to 10,000 by 12,000, that is 5/6. What does it mean? Fifth bright band due to the first wavelength coincides with the sixth bright band due to the second wavelength. See, if the fifth band of the first pattern and sixth band of the second pattern coincide, then 10th band of the first pattern will coincide with the 12th band of the second pattern. Okay, 15th bright band of the first pattern will coincide with the 18th bright band of the second pattern. But we have to get the distance, minimum distance from the center where the two bands coincide. Okay, that will be the distance of the fifth bright band from the center of the screen due to the first wavelength. Okay, so we will get this n1 lambda 1 capital D by small d, where n1 equal to 5 and lambda 1 equal to 12,000. So 12,000 angstroms we can convert to meter by multiplying with the 10 raised minus 10, and capital D is 2 meter, small d that is 2 millimeter, 2 into 10 raised minus 3, we will get 6 millimeter. Okay, see, this is the distance of the fifth bright bands from the center of the screen, okay, due to the first wavelength. Okay, so this will be 6 millimeter, right? In Young's double slit experiment, the fringe width is found to be 0.4 millimeter. If the whole apparatus is immersed in water of refractive index 4/3 without disturbing the geometrical arrangement, the new fringe width will be. See, when the system is shifted from vacuum or air to another medium, wavelength will change. Wavelength will become, will change from lambda to lambda by mu. So the bandwidth also will change. Bandwidth in air or in vacuum will be lambda capital D by small d, and wavelength bandwidth in another medium will be beta dash equal to lambda dash capital D by small d. Lambda dash we can write lambda by mu. Okay, so ultimately beta dash bandwidth in a medium will be equal to beta by mu. bandwidth in air divided by refractive index of the medium. In air we have 0.4 millimeter, and the refractive index of medium, that is water, it is equal to 4 by 3. So it will be 0.3 millimeter. 0.3 millimeter. Okay. Two Polaroids P1 and P2 are placed with their axis perpendicular to each other. Okay, see the angle between the first Polaroid, it is kept like this, and the last Polaroid is kept like this. The angle between them is 90 degree. Okay, first Polaroid is like this and last Polaroid is like this, perpendicular to each other. Now a third Polaroid is kept between them, so that it makes 45 degree with each of the first and last. Okay, so unpolarized light is allowed to incident on the first polarizer. So the intensity of light transmitted by it will be half of the incident intensity, means I1 equal to I0 by 2. Okay, now see the angle between the axis of the first and second crystals, that is 45 degree. So by Malus law, I2 equals I1 cos square 45. Where I1 is the intensity of light incident on the second polarizer, and I2 is the intensity of light transmitted through it. Okay, so here we have theta 45 degree, cos 45 1 by root 2, cos square 45 1 by 2. So it will be I0 by 2 times half, so I0 by 4. Okay, now see the intensity of light incident on the third polarizer is I2, and the intensity of light transmitted by it is I3. Okay, so I3 equal to I2 cos square 45 by Malus law. Okay, and we will get I0 divided by 8. I0 by 8. The ratio of resolving powers of an optical microscope for two wavelength lambda 1 4000 angstroms and lambda 2 6000 angstroms is. See, resolving power for a microscope. Yeah, that is 2 mu sin theta divided by lambda, and 2 mu sin theta is called a numerical aperture. Anyway, resolving power is proportional to 1 by lambda. So resolving power for the first divided by resolving power for the second, that is equal to lambda 2 by lambda 1 equal to 6000 by 4000, that is 3:2. This one. Okay.